Good morning, dear students. I am Professor Anand Raja, Department of Mechanical Engineering, PR Pote Patil College of Engineering and Management, Amravati. First of all, I would like to welcome you all for the course of Refrigeration and Air Conditioning for 8th SEM Mechanical Engineering. See, basically this particular subject RAC, which we generally used to call, this is one of the important subject of mechanical engineering. Okay, you might have, you all are familiar about this particular word refrigeration as well as the air conditioning, right? From your domestic use to the industrial applications. In many industries, in many places, you have gone through this refrigerators, chillers, freezers, air conditioners. Okay, so this is one of the important subject of mechanical engineering which belongs to the thermal side. As you all of knowing, the mechanical engineering that can be categorized in designing, manufacturing, and one of is the thermal. So this subject also belongs to the thermal side, just like your thermodynamics, heat transfer, then energy conversions, IC engines. So similarly, you have this particular subject that is refrigeration and air conditioning. So in this particular course, today we will start your unit number 1, that is fundamental of refrigeration and introduction to your VCR system. So let's begin. So before going to the exact portion of this VCR system or fundamentals, let us go through the outline of this particular unit, that is content. So first we should know what exactly an refrigeration is, then the difference between the refrigeration and air conditioning, then the coefficient of performance, tons of refrigeration, then we will deal with the vapor compression refrigeration system, and last what we will cover, that is factors affecting the performance of VCR. So this is what the outline of your unit number 1, this is what the 6 topics we will have to cover in this particular lecture. Okay, now let us start with the first part, that is what is refrigeration. Now it is simply an outcome of second law of thermodynamics. If you remember, in second law of thermodynamics, we have gone through two statements. One is a Kelvin-Planck statement and one is a Clausius statement. Okay, you can recall these laws of thermodynamics. We started with the zeroth law of thermodynamics. Okay, that deals with the thermal equilibrium condition. Then we have gone through the first law of thermodynamics, that was about the equivalent conversion of heat and work and vice versa. Okay, and after that, due to some limitations of first law, that it is not prescribing the direction of processes, it is not exactly giving you the quantity of conversions. So that's why we have generated the second law of thermodynamics, where we got two statements. Okay, one is a Kelvin-Planck statement and one is a Clausius statement, and both are having particular direction, both are giving the particular direction to any thermodynamic process. And basically the two direction what we are having for this particular energy conversion, one is the heat is flowing from higher temperature to lower temperature, and one is from lower temperature to higher temperature. Now Kelvin Planck statement, it is basically dealing with your flow of heat from higher temperature region to lower temperature region. Okay, from higher energy reservoir to the lower energy reservoir, from source to sink. Okay, and when this heat is flowing from higher temperature region to lower temperature region, we are extracting some heat and converting that heat into work. Okay, and this is what the Kelvin Planck statement is. Whereas when you are talking about the Clausius statement, it is exactly opposite to your Kelvin Planck. Okay, what we did in the Kelvin Planck, we have transferred the heat from higher temperature region to lower temperature region, and when it is flowing, we have used some heat and converted some heat into the work. Now we will go in the opposite direction, in the reverse direction. Now if I wanted to transfer the heat from lower temperature region to higher temperature region, I need to supply some work, because this is not a natural phenomena that heat will flowing from lower temperature region to higher temperature region. It is only in higher to lower value. Okay, it is a natural phenomena. Heat will always flow from higher temperature region to lower temperature region. That deals with your Kelvin Planck. Okay, that's happening naturally. Simply if you are taking a cup of a coffee, you are keeping it on table. Okay, it is at 70 degrees Celsius. After some span of a time, you will observe that its temperature is get reduced. Okay, it's naturally happening because your surrounding temperature, maybe it is 30, 35. Your coffee, it's having a temperature of 70 degrees Celsius. So your coffee is going to release the heat, Okay, it is losing the heat, and that air that's surrounding it is absorbing that heat. Okay, and this heat transfer, it will be continuing till both the mediums or both the substance are getting the same temperature, that is 35 for an example. Okay, so this is a natural phenomena, we don't need to do anything in that. Okay, and whenever such flow is taking place, we can utilize that heat and we can convert it into the work, that is Kelvin Planck said. Okay, and if you want to transfer the heat from lower temperature to higher temperature, okay, in that case it will not be possible naturally. Okay, you will have to supply some work in that. According to these two statements, one is Kelvin Planck and one is a Clausius, we got this two outcomes. One is a heat engine and one is a refrigerator or heat pump. When I'm talking about the heat engine, it is all kind of a prime movers, all kind of a device, okay, or machines which are developing the work, which are producing some work. You may have turbine, you may have some steam turbine, gas turbine, okay, your IC engines, okay, that is petrol engine, diesel engine, all they comes into the category of heat engine, that is Kelvin Planck statement. Whereas when I'm talking about the refrigerator or heat pump, they are the work absorbing devices. Okay, they consume some work in order to transfer the heat from lower temperature to the higher temperature. So your refrigeration or your refrigerator or any air conditioning, they comes into the category of Clausius statement. That's why refrigeration is nothing but an outcome of second law of thermodynamics. Okay, so that's why if you'll see this statement for Clausius, that it is essential to supply some external work to transfer the heat from lower temperature region to the higher temperature region. And you can have this particular sketch also. Okay, we have two reservoirs. One is at temperature TH, that is higher temperature reservoir or higher temperature, we can say source, and one is TL, that is a lower energy reservoir. And between that we had this particular device, that is refrigerator, which is consuming the work in order to transfer the heat from lower energy reservoir to higher energy reservoir. Okay, if I'm supplying this W amount of work, then only I can extract QL amount of heat from this reservoir in order to make its temperature lower than surrounding temperature. Okay, and altogether whatever the heat you have extracted, we have sending it to the thermal reservoir, which is at higher temperature, and we also call them as a source and the sink. Okay, so this can be cleared that when you are talking about the Clausius statement, heat should be flowing from lower temperature to higher temperature. In this case, whatever the example you have shown, your reservoir is nothing but your TH reservoir, that is nothing but your atmosphere, and the reservoir which is at TL temperature, this is nothing but a confined space where you want to create the refrigerating effect. Okay, where you want to produce a temperature lower than the surrounding temperature. Okay, same example what we have taken, that is for a coffee from 70 degrees Celsius to 35 degrees Celsius, that is the Kelvin Planck statement. Heat is flowing from higher temperature to lower temperature. But if I want to make that coffee to have its temperature, let me say 10 degrees Celsius, I'll have to keep it in the refrigerator. You can't have the natural process for that. So if you'll define the refrigeration, it is a science of producing and maintaining the temperature of a substance or a confined space below the surrounding temperature. This is very important, surrounding temperature. Okay, if you are the see, sometimes people get confused about the cooling and the refrigeration. Okay, they said refrigeration means cooling. It is not like that. Every refrigeration process you can call it as a cooling process, but not all cooling process can be termed as a refrigeration. Okay, coffees get cooled, okay, from 70 to 35. This is cooling, you can say that this is the natural phenomena. Why? Because it reaches to certain temperature which matches to your surrounding temperature. It reaches to certain thermal equilibrium conditions. Okay, but if I want to produce a temperature lower than surrounding temperature, then I'm talking about the refrigeration. That's why it is a definition that it is not simply producing but maintaining also. First you will have to produce, first you will have to extract the heat, and then maintain that particular temperature below than the surrounding temperature. That is the refrigeration is. Again, we can take it this simple example. Let me say this is a confined space, and let me say TA is a temperature of air, the surrounding temperature. that is 40 degrees Celsius. And this confined space right now at this moment, it is also having the temperature of 40 degrees Celsius. This is surrounding temperature. And let me say if I want to produce a temperature here 5 degrees Celsius. So what I have to do? First I have to extract the heat. Okay, first I have to produce that 5 degrees Celsius, then I'll have to maintain it. So for maintaining or for producing, first we will have to extract the heat from 40, it should reach to 5 degrees Celsius. Okay, obviously your T and TA, T is always lesser than your TA. TA is a surrounding temperature. Okay, so two reservoirs what we have taken in the previous case, that is TL and TH. So here TL is nothing but temperature of your confined space, that is the lower temperature, that is 5 degrees Celsius, and TH, that is a temperature of your surrounding. Okay, that is higher energy reservoir, higher temperature reservoir. Okay, so in other words, you can say that refrigeration means continuous extraction of heat from a body whose temperature is already below the temperature of its surrounding. First you have produced that lower temperature, then surrounding, and then you have maintained it. How? By continuous extraction of heat. Okay, and this continuous extraction of heat is nothing but your desired effect or refrigerating effect. Now one more important thing, that desired effect or refrigerating effect. Desired effect is nothing but your the effect which you required in that confined space. According to the second law of thermodynamics and Kelvin Planck's in Clausius statement, see, I've said that there are two outcomes for this particular Clausius statement. Either it is a refrigerator or it is heat pump. So if I'm continuously extracting the heat, okay, and my focus is of that lower temperature, then I'm talking about refrigerator. Now my desired effect would be cooling or refrigerating. And again I'm continuously extracting the heat, and my purpose is to send that heat somewhere I need a warmer effect. Okay, that is nothing but another desired effect, that is of heating. So if I'm talking about the cooling effect, if I'm focusing on the lower temperature that has to be maintained, then I am talking about the refrigerator. And if I'm talking about the extracted heat needed to supply somewhere for creating the heating effect, then I'm talking about the heat pump. Cycle would be same, directions would also be same, only focus is different. In heat pump, focus is on TH temperature, and in the refrigerator, focus is on the TL temperature, that is lower temperature. Now next thing is about difference between refrigeration and air conditioning. This is also an important thing, because sometimes we always say that refrigeration is lowering the temperature, and some may get confused about air conditioning also. They said that air conditioning is also reducing the temperature. It is not like that. First thing, make it sure when you are talking about refrigeration, it is always deals with the temperature lower than surrounding temperature. You have freezers, you have your refrigerator, industrial or maybe domestic. Anywhere, whenever you are speaking about refrigeration, means it is dealing with a temperature lower than surrounding temperature. But when I'm talking about air conditioning, it is lower or higher than surrounding temperature, depending upon the comfort conditions. Now if I'm talking about the summer, obviously my temperature requirement in the room in that particular space is lower temperature. But when I'm talking about the winter conditions, I need to maintain the temperature more than the surrounding temperature. Okay, so when you're monitoring the temperature may be lower or higher than the surrounding temperature, then it can be possible in your air conditioning. Okay, so make it sure refrigeration, it always deal with the lower temperature, but air conditioning, it may be higher or it may be lower. This is first thing. Second thing is about the parameter which you are controlling. Okay, refrigeration, only one parameter you are going to focus on, that is temperature. But when I'm talking about air conditioning, it is along with the temperature, you need to control the humidity also. Also it comprises with the concept of your purity and the circulation of air also. So simultaneous control you will have to make it. Simultaneous study you will have to deal in the air conditioning, that you will have to maintain the temperature, you will have to maintain the humidity. There must be proper purity of air, proper circulation of air. So this is what the controlling parameter of your air conditioning. Whereas in refrigeration, only one thing we are talking, that is temperature, and that should be lower than surrounding temperature. And when you're talking about the application, mostly when you're talking about the refrigeration, it is used for perishable items, the items which you can't keep it in the surrounding for a longer span of a time. Okay, they may get spoiled. That's why to preserve them, to preserve the perishable items, you'll have to use the refrigeration. Okay, sometimes it used in the industries also for some chemical, textile, or some other industry, process industries also. Okay, and when I'm talking about the air conditioning, mostly it is for human comfort, and that also depends on the climatic conditions. So that is what the comparison or difference between refrigeration and air conditioning. Now, by taking the same example what we have taken previously, we'll try to find out the performance of this refrigeration system. Okay, so we have source, that is atmosphere, that is at TH temperature, and sink, that is at TL temperature, that is lower temperature, which is I'm going to focus now. See, when I'm supplying this W amount of work to this particular device, that is refrigerator, okay, it will be able to extract the heat, that is QL. And altogether the QH amount of heat, whatever the heat after extracting the heat from sink, you will send it to the source. My sink, that is nothing but confined space which I need to maintain at 5 degrees Celsius. Source is nothing but atmosphere which is at 40 degrees Celsius. And this is the work input, the work which you are consuming, the work which you are supplying to the refrigerator, so that it will extract some heat. Okay, whatever the heat you have extracted, that is nothing but you are producing the desired effect. Okay, the quantity of heat what you have extracted, that is equivalent to your desired effect, that is the refrigerating effect or cooling effect. And after that, whatever the heat you have extracted, you will have to send it to the source, that is atmosphere. Now COP, simply it is the ratio of your desired refrigerating effect upon work spent in producing the refrigerating effect. Okay, QL upon WN. Now this is simple calculate. Already you in thermodynamics you have gone through this particular part. That is desired effect upon work supplied. So this is what your COP, and always its value would be more than 1. One more thing that is about COP regarding the performance of any system, any device, either you have efficiency or you may have COP. So efficiency, it would be coming into the picture whenever you are talking about the conversion of energies. Okay, one form of energies get converted into another form. Then we can speak about the term efficiency. Then you can take it as 100%, below than 100%. The maximum limit is 100%. No ideal machine we have in the nature that gives you the 100% efficiency. Okay, so the reference is of 100%, and we'll get some conversion rate, maybe 60%, 70, 80. Okay, so that is about the efficiency. But when you are talking about the COP, it is not about the conversion. It is simply about the transfer of energy. Efficiency means conversion of energy, converting the energy, and COP, it is transfer of energy. Only heat we have transferred from lower to higher by supplying some work. And second important thing is about the inputs. In case of your refrigerator or heat pump, your input is the mechanical energy, the mechanical work you have supplied, compressor work. Okay, so this energy, mechanical energy, what you're talking, the work what you're talking, it is a high grade energy. It is a superior form of energy. Whereas when I'm talking about the efficiency, my input is nothing but the heat energy. Okay, heat engine, when I'm talking about here, and input is heat energy, and it is get converted into some work. So from, if you're supplying the inferior energy, okay, that is heat, which is a low grade energy, you can't fully convert it into the work, which is a superior energy. So that's why always remember your COP will be greater than 1 and your efficiency would be lesser than 1. So that's about the COP. Now next term is about the tons of refrigeration, or you can say that it is a standard rating of any HVAC system. HVAC, that is heating, ventilation and air conditioning. All the components which work on a Clausius statement. It may be your heating application, or it may be for cooling application. Always whenever you are going to compare them, you will have to compare them on the basis of their rating, that is tons of refrigeration, or in terms of TR. Okay, you might be familiar with this term TR. If you go to any particular showroom for purchasing any AC, okay, they used to ask about 1 ton, 2 ton, 1 TR, 2 TR, 1.5 TR, and suddenly they ask you about the size of your room, and accordingly they have their standard specification sheet. According to that particular size of the room, they'll suggest you that you take it for one ton of refrigeration, 1 TR AC, you take it. So what exactly that is? So by this example you will get it clear. Let me say if I am having 1 ton of ice. Now this is 2000 pounds, that is in the American standards. Okay, and we'll convert it into the kgs. That would be around 900 something. So 1 ton we have, let me say 1000 kg of ice. This 1000 kg of ice, okay, it is going to produce the cooling effect when it gets starts melting. Okay, and when I'm having this 1000 kg of ice and I'm supplying some warm air over here in order to melt it, in order to melt that particular ice, it will consume some heat. And when this heat is utilized for converting the phase change, we generally used to call it as a latent heat. And the latent heat of ice for this particular conversion from ice to water, that required around 335 kilojoule per kg. Okay, and same particular 335 kilojoule per kg, if I'm applying it for this 1 ton of ice, by prescribing some time limit, I'll get it the 1 ton of refrigeration like this. Okay, obviously for 1 kg it require 335. So for 1 ton it require 1000 into 335, and if I'm providing the time limit of 24 hour, for 1 TR I can write it down like this: 1000 multiplied by 335 divided by 24 into 60, that is 232.6 kilojoule per minute. And if you'll take it in the seconds, you will get it around 3.5 kilowatt. So that is its cooling effect, cooling capacity. Okay, how much heat it can extract. If I'm talking about the 1 TR, I'm talking about the 1 TR of AC, that is extracting 3.5 kilowatt of heat. 1.5 TR simply multiplied with that 3.5. 2 TR multiplied with by 3.5 kilowatt. You will get it that this much amount of heat this particular system can extract. So if you'll go for the definition, 1 ton of refrigeration is the amount of heat transfer rate required to melt 1 ton of ice from and at 0 degrees Celsius in 24 hours. From and at 0 degrees Celsius, because we are dealing with the phase change, a latent heat we are talking about. So the temperature will not change. It would be as it is. From 0 degrees Celsius ice to 0 degrees Celsius water in 24 hours, how much energy it transferred, that is 232.6 kilojoule per minute. For practical applications, for numerical, we used to take it 210 kilojoule per minute. Okay, this is the practical unit of refrigeration. Now we will move towards the most important part of your refrigeration system, that is VCR system, vapor compression refrigeration system. This is one way of producing the refrigeration. There are multiple ways. From ancient time, if you are talking about, right from harvesting the ice, right from utilizing some easily available fluid, that is air refrigeration system, we finally reach towards the most useful method of producing the refrigeration, that is vapor compression refrigeration system. Okay, vapor compression refrigeration system, here we are talking about the working fluid, okay, which is continuously changing its phase from one thermodynamic system to another thermodynamic system, and by changing its phase it is able to extract the heat. Okay, we know the working fluid, it is different for every different systems. For steam engine, for steam turbines we have steam, for gas turbine you have a gas as a working fluid. Okay, so here we are having the working fluid, that is the refrigerant, okay, which is having some prescribed properties, desirable properties, boiling point, melting point, then it's latent heat, okay, thermal conductivity, specific heats, and some other chemical, physical, and thermodynamic properties. Multiple properties are there. So here in vapor compression refrigeration system, we are going to have four important components. One is a compressor, second is a condenser, next is the expansion device, and last one is the evaporator, where we are going to produce the desired effect. All four are the open systems. Okay, thermodynamics, because their same working fluid is circulating in these four particular components, from compressor to condenser, condenser to expansion device, from expansion device to your evaporator, and again returning back to the compressor, and cycle would goes on. So now here we will deal with this vapor compression refrigeration system, and before that we'll have to consider some assumptions. Okay, because whatever the thermodynamic process in those particular open system will takes place, they will be bounded with some standard assumptions, standard ideal assumptions, ideal things, okay, for this ideal vapor compression cycle. Likewise, irreversibility within the evaporator, condenser, or compressor are ignored. Okay, all processes would be reversible in nature when I'm talking about the ideal cycle. Practically that would be not possible, because every process will associated with some losses. That may be heat losses, that would be frictional losses, that would be drop in pressure, but all we are neglecting here. We are talking about an ideal cycle. So whatever the irreversibility is there, we are ignoring that. We are saying that, we are assuming that all processes are reversible, whether it is a compression or it is condensation or evaporation. This is the first assumption. Second, there is no frictional pressure drop. Okay, because we will consider that the processes that is taking place in condenser and evaporator, that is the heat transfer processes, they are constant pressure process. Though in practical manner there would be not like that, but in ideal case we are saying that there would be no frictional pressure drop. Okay, refrigerant flow at the constant pressure through the two heat exchangers. Okay, that is constant pressure. The pressure of your refrigerant, that would be constant in evaporator as well as in the condenser. Again, heat losses to the surrounding, again it is ignored. We'll say that whatever the heat transfer devices are there, they are perfectly insulated. Again, it is a assumption. And last one, the compression, it should be isentropic, reversible adiabatic compression. No frictional losses, no heat losses. Only there is a constant entropy. That is perfectly reversible process. So after having these assumptions, we can utilize these assumptions for different thermodynamic system, different open thermodynamic system in VCR cycle. Okay, now let us take that VCR system. Now here I am having the compressor. Now again, in previous semester, in 7th semester, you have studied the EC2 subject. Okay, there we have gone through the different types of compressors. Now again, depending upon the pressure, depending upon the discharge, you may go for reciprocating compressor, you may go for the rotary compressors also. Again, it is finally depending upon the cooling effect, desirable effect, capacity of your plant. Accordingly, we'll go for either centrifugal, either rotary, or you may go for the reciprocating compressor. Now you can see that A and B. A is nothing but, A section is nothing but for your suction portion, suction walls would be present there, suction ports, and B is nothing but your delivery port. This particular compressor, it will receive the low pressure vapor. These vapors would be coming from the evaporator. Okay, always remember, whatever the outcome of this evaporator is, it must be in the vapor form. Okay, if it is in the vapor form, you can predict that the cooling effect has been produced as required. Okay, this low pressure vapor that is entering to your compressor, then you will have an isentropic compression. Just now we have assumed that reversible adiabatic compression. So after compression, you will get the high pressure vapor. At both the point at A as well as at B, you are having the vapor. Only difference is that after compression, you have high pressure, high temperature, superheated vapor. Okay, that is desirable. This vapor, you will send it to the condenser. This is another important component of your VCR system, that is heat rejection device. Whatever the refrigerant which is coming out of your compressor, which is at high pressure and high temperature, now you are condensing it into the condenser. Now you can use any cooling media, that would be air, that could be water also. Again, finally it depends upon the capacity of your plant. Okay, if you are having the low capacity unit, domestic refrigerator if you are talking about, you don't need to use any uh, other working fluid than air. Okay, so this is the condenser where your high pressure, high temperature, superheated refrigerant, superheated vapor refrigerant, it would be condensed. Pressure would be constant. Already we have assumed that whatever the heat transfer process will takes place, that is at constant pressure. So at the inlet of condenser or at the exit of condenser, you will have same pressure, that is high. Only difference is that at the inlet you have superheated vapor and at the exit you will have liquid, and that particular liquid you are going to store it in the receiver. From receiver, now this is just a collection tank, you can see that, okay, where your refrigerant is get collected in the liquid form, and this pressurized liquid, that is high pressure liquid, high pressure liquid refrigerant, it comes out of your receiver and it goes to your expansion device. Now expansion device, that is nothing but your capillary tube. Okay, when you're talking about the domestic refrigerator, you may have thermostatic expansion valve, automatic expansion valve. Okay, in some cases there would be a manually operated valve. Its main purpose is to reduce the pressure. Okay, the pressure which is required in your evaporator, so that maximum heat transfer should be possible. For reducing that pressure, we are having the expansion device. Now at the entry of your expansion device, you are having the high pressure liquid, whereas when you are going to have an expansion, when you are going to reduce its pressure, you will have the low pressure. Now the low pressure is not purely liquid. When you are expanding, there is some sort of vapor particle, vapor droplet, vapor molecules would also be present there. Okay, so after expansion, you have reduced the pressure and you got liquid plus vapor mixture, and this particular mixture you will send it to your evaporator. Now evaporator, it is the evaporator coils, what you are observing, it is kept in a confined space, the well insulated place. Okay, where we are going to produce the refrigerating effect, where the temperature would be lower than surrounding temperature. And at the last, after absorbing the heat from the substances or from the products which you kept in that particular space, your liquid refrigerant, it would be converted into vapor form, and again it would be sent back to your compressor. So accordingly the cycle will start: compressor, condenser, expansion device, and your evaporator. In simple domestic refrigerator, if you're observing on the backside of your refrigerator, there is a black coils. Okay, if you have observed carefully, this is nothing but your condenser tubes. Okay, at the lowest portion of your refrigerator on the back side, there is a compressors. Okay, that could be scroll type compressor. Then expansion device. For domestic use, for any training machine, you will have to use the capillary tube. That also you have seen, a small diameter and long length tube that is kept in the coiled manner, that arranged in the coiled manner. That is nothing but your expansion device. And the evaporator, that is nothing but the freezer section of your refrigerator. That's what about the four important components. You can give the numbering to this particular points at the entries and the exit of different systems, so that you can easily plot this particular processes. 1 to 2 compression, 2 to 3 condensation, 3 to 4 that is your expansion, and 4 to 1 that is evaporation. Okay, now same four processes we will plot it on the property diagram. Remember, 1 to 2 isentropic compression, 2 to 3 constant pressure heat rejection, 3 to 4 expansion. This is isenthalpic expansion. Make it sure this process is very rapid process. Whatever the expansion process is taking place, this is irreversible process, and this is happened in this very short span of a time. That's why this is irreversible process, and this is isenthalpic process. Enthalpy at point 3 is equal to enthalpy at point 4. It is simply flow. There is no heat transfer, there is no work transfer. Okay, for other devices you can calculate either heat or work, heat transfer or work transfer, but for expansion device your heat transfer would be 0, work transfer that is also 0. Only there is drop in pressure at constant enthalpy, that is H3 is equal to H4, and 4 to 1 again it is constant pressure heat addition process. Now same 4 processes we will plot it on the property diagram. I'm having TS diagram, temperature versus entropy, and another one is a pH diagram, that is pressure versus enthalpy. 4 processes we have written at the below: isentropic compression, isobaric, that is constant pressure heat rejection, isenthalpic expansion, and 4 to 1 isobaric heat addition. Now this is your saturation curves. Okay, at top you can, in TS diagram you can see that dome type, that particular arrangement. At the top you will have the critical point. On the left side of that critical point, this is saturated liquid, and on the right side that is saturated vapor, dry saturated vapor. Now let us look at point number 1 at first. Point number 1, what you have said, that is the entry of your compressor, and at the entry of compressor, let us say that your refrigerant, it is in the vapor form and it is at the lower pressure. So point number 1 I have marked here on saturated vapor line, dry saturated vapor line, we have point number 1. Now from point number 1 we will go for the isentropic expansion as per the assumption we have made. Isentropic means constant entropy. The entropy at point number 1, that is at the entry of compressor, is equal to entropy at point number 2, that is exit of your compressor, and you can locate point number 2 and you can show this line 1 to 2 on pH and TS diagram. 1 to 2 is isentropic compression. S1 is equal to S2. Okay, now at point number 2, where you are in the superheated region. Point number 1, you are in the dry saturated line, X is equal to 1, and point number 2, you are having superheated vapor. Now this superheated vapor, now it enters to your condenser, where the condensation will begin. Now this is at the constant pressure. Process 2 to 3 is of condensation. At first, from point number 2 we will reach to the dry saturated curve. This is the removal of superheat, and after removal of superheat, okay, some temperature is dropped, and after that we have gone for the exact condensation at constant temperature, exact phase change. Okay, point number 2 is it is in the superheated region, and point number 3 it is the saturated liquid. 2 to 3 is your constant pressure heat rejection process. Okay, after that you will go for expansion. As I have said that it is isenthalpic, so enthalpy at 3 is equal to enthalpy at 4. You can see it on the pH diagram, 3 to 4 vertically downward line. Okay, 3 to 4 is nothing but your isenthalpic expansion process, and after that 4 to 1, that is your evaporation process, where you will get the refrigerating effect. Now this is what the VCR cycle, vapor compression refrigeration cycle. 1 2 3 4 1 1 to 2 compression, 2 to 3 condensation, 3 to 4 expansion, and 4 to 1 evaporation. Now for these 4 processes we can have the thermodynamic analysis like this. For compressor we can calculate the work, that is H2 minus H1. How much heat is rejected, that is QR is equal to H3 minus H2. For expansion we know that H3 is equal to H4 because this is the constant enthalpy expansion, isenthalpic expansion, and 4 to 1, that is heat extraction or heat addition. that is QA is equal to H1 minus H4. Now this heat addition, that is QL, heat rejection, that is QH, and WC is nothing but your work input WN. Now by using these values, of heat transfer and the work, you can calculate the COP. Now how to get the values of enthalpy? For getting the values of enthalpy, we have the pH chart. Okay, the layout of pH chart we'll see now. On y-axis there is pressure, and on x-axis there is enthalpy, and the two lines would be there, one for saturated liquid and one is for saturated vapor, like this. Okay. For each refrigerant it would be different properties are there, so different pH chart you will have, but all will have the same layout like what we are seeing right now. So y-axis there is pressure, on x-axis there is enthalpy, one is saturated liquid line, one is a dry saturated vapor line. Between them there would be dryness fraction line, because at saturated liquid line dryness fraction is 0, x is equal to 0, and at dry saturated vapor line x is equal to 1. So 0 to 1 you will have number of lines, just like the line what you are observing, dryness fraction line, it is having the dryness, like let me say x is equal to 0.1, means it is a 10% dry, 90% weight. So there would be 0.1, 0.2 up to 0.9. Okay, under this dome, under this particular two line, if you are having your refrigerant, it means it is in the mixture form. It is the mixture of liquid and vapor. On saturated liquid line, it is purely liquid, x is equal to 0. On dry saturated vapor line, x is equal to 1. No liquid, only vapor, and in between them you will have some amount of liquid, some amount of vapor. Obviously these are two lines parallel to x and y axis, that is constant pressure line and constant enthalpy line, from where you can get the values of enthalpy in order to calculate the compression work or heat transfer rates. And this is the curve, this is for the constant temperature line. This particular line what you are observing, vertical line, horizontal line, and this curve, this particular lines, they are representing a fixed value of a temperature. Okay, so if you have a temperature of, let me say 5 degrees Celsius, so you will have to make it sure where it could be, whether it is in the liquid form, whether it is in the some dryness, or it is in the superheated form. Okay, so this is what the layout of your pH chart. Again, two more things are there. One is a constant entropy line, okay, and one would be specific volume line. They would be used when you are going for the compression. Then how the specific volume is changed, how you maintain the entropy constant. For following the path of compression parallel to the constant entropy, you will have to use this particular lines. Or you can see this liquid region, two phase region, that is mixture region, liquid plus vapor, and the superheated vapor region. In textbooks you can see this kind of a sketch also for this pH chart. Critical point, saturated liquid line, saturated vapor line, superheated region, subcooled region, weight vapor region, and the critical pressure. Now we will see the different factors which will affect the performance of VCR system. Let me say if I am having standard pressure, suction pressure 1 bar, discharge pressure 8 bar, okay, and accordingly this is the pressure lift from 1 bar to 8 bar. You will have to maintain the pressure in the condenser and the evaporator. So what we are trying to do, we are trying to examine that what will happen if you are going to reduce the suction pressure, and what will happen if you are going to increase the discharge pressure. What would be its effect on the performance of VCR system? What would be effect on the COP? Same way, whether it is desirable or not to go for superheating and subcooling. Superheating, there must be vapor refrigerant that should be there at the exit of compression, and sometimes at the entry of compression also. That is effect of superheating. And subcooling, after condensation, when you reach to the saturated liquid, okay, you must have some more drop in temperature at same pressure, so that the performance can be examined. So let us see this few parameters. First one is effect of suction pressure. Now this is the standard cycle: 1 2 3 4. 1 to 2 compression, 2 to 3 condensation, 3 to 4 that is your expansion, and 4 to 1 that is evaporation. Now what I'm trying to do here, I'm going to reduce the suction pressure. I'm trying to take the reduction in the suction pressure and I'll try to find out what is its effect. You can simply read, if you are reducing the suction pressure, specific volume will increase, work required that is also increase. Ultimately, as your work is increased, there is decrement in the COP, and ultimately you have also seen on the pH diagram there is drop in the refrigerating effect also. Okay, let us see that particular. Now this is PS pressure, which is standard suction pressure, and I'm trying to reduce it. Earlier it was 1 bar, now I am trying to take it 0.9 bar or 0.8 bar. What happens if I am reduce this suction pressure? Now point number 1, it is shifted somewhere here and compression would be like this, 1 to 2 dash or 1 dash to 2 dash. Earlier you can see the compression 1 to 2. If I am taking enthalpy at 1, enthalpy at 2, I'll get some H2 minus H2 minus H1, that is work of compression. But if I have reduced the suction pressure, now I'm getting point this 2 dash, and if I am taking 2 dash minus 1 dash, you will get more amount of compression work. And at the same time, point number 3, its position will not change at all. Only point number 4, now it is shifted to 4 dash like this. Now you can see this new cycle by reducing the suction pressure. 1 dash to 2 dash, compression work increased. As I've reduced the suction pressure, work of compression is increased. Why? Because specific volume is also increased. Then 2 dash to 3 dash, your condensation will take place. 3 dash to 4 dash, 3 to 4 dash, you will have expansion. And when you are reaching to 4 dash, okay, from 4 dash to 1 dash, if you will take that particular difference, you'll observe that refrigerating effect, this value H1 dash minus H4 dash, it is lesser than H1 minus H4. Ultimately what has happened, your input is increased, compression work is increased, but your desirable effect, that is refrigerating effect, it is decreased. So ultimately your COP is reduced, and you can conclude that refrigerating effect is decreased, work required is increased. The net effect is to reduce the refrigerating capacity of the system and ultimately the COP. Now next is effect of discharge pressure. In previous case we have tried to reduce the suction pressure, and now we are trying to increase the discharge pressure, this PD pressure. Earlier it was, let me say, 8 bar, now I am trying to take it as a 10 bar. If I am taking the 10 bar, my inlet would be as it is, point number 1 would be as it is, only point number 2 would be shifted like this. Again it is isentropic, that's why both are overlapping on each other, coinciding on each other. So this is point number 2 dash. Now simply you can see here, refrigerating effect would again decrease, because from 2 dash I will go for condensation, and 3 dash would be your end of condensation, and after that when you will go for the expansion, you will get point number 4 dash. Earlier your refrigerating effect from 4 to 1, now your refrigerating effect is 4 dash to 1. Refrigerating effect is reduced. Okay, now talk about the compression work. Earlier your compression work was 1 to 2, H2 minus H1. Now after increasing the discharge pressure, when you have 1 dash to 2 dash, your compression work is 2 dash minus 1, which is more than H2 minus H1. So here also you have increased the pressure, it means there is increase in the compression work, decrease in refrigerating effect, ultimately there is a decrease in the COP. So this is also not desirable. Just like your reduction in suction pressure, similar to that, increment in the discharge pressure, this will also not increase your COP. Okay, So only the difference is that between reducing the suction pressure and increasing the discharge pressure, that the effect of decreasing the suction pressure is more predominant than the effect of increasing the discharge pressure. Okay, obviously H2 dash minus H1 is greater than H2 minus H1. Our aim is to reduce the compression work, but here we have increased the compression work. Our aim should be increase the refrigerating effect, but we have decreased this. Now next is effect of superheating. In superheating, what I've said, that the inlet to your compressor, that should be also in the superheated form. In conventional cycle 1 2 3 4 1, point number 1, it is at the dry saturated vapor. But when I'm talking about the superheating, point number 1, it should also lie in the superheated vapor region like this. Now compression, it is superheated type 1 dash to 2 dash. Rest would be as it is, there would be no any change. To 1 dash to 2 dash, 2 dash to 3, 3 to 4, and 4 dash to 1. But when you do this, again your refrigerating capacities also get decreased. Compression would be increased, refrigerating effect would be decreased, and ultimately COP, that is also get decreased here. Effect of superheating is to increase the refrigerating effect, but this increase in refrigerating effect is at the cost of increasing amount of compression work spent to attain the upper pressure limit. 1 to 2 also we have reached to the same pressure, 1 bar to 8 bar. 1 dash to 2 dash also we have reached from 1 bar to 8 bar. Okay, but more amount of work you will have to supply because specific volume is changed. Okay, and since the increase in the work is more compared to increase in the refrigerating effect, therefore the overall effect of superheating is giving you the lower value of COP. So the last one is nothing but your effect of subcooling. Now in effect of subcooling, what we are trying to shift this point number 3 in the subcooled region. We are trying to extract more heat from that. More cooling it should be provided. More condensation should be done. So 1 2 3 4, that is your conventional cycle. Now what I'm trying to do, I'm not disturbing the evaporator, I'm not disturbing the compression, I'm just trying to change that point number 3. From 2 to 3, I must go for 2 to 3 dash. Now extra cooling coil you can use. Okay, that after condensation at constant pressure, you change the phase from vapor to liquid. Even after reaching to the saturated liquid, again you cool it more, so that you will reach to point number 3 dash. And when you reach to point number 3 dash, then you should go for expansion, and after expansion you will get 3 to 4 dash. Now 4 dash is a desirable point, because you make it sure what you are supplying to evaporator, it must be liquid. Practically it is not possible you get it liquid plus vapor, maybe 80% liquid and 20% vapor. So you should try to have more amount of liquid. So at point number 4, you have maybe 80% liquid, 20% vapor. But at point number 4 dash, I may have 90% liquid and 10% vapor. So this is desirable. More amount of liquid is entering to your evaporator. So more the liquid you are supplying, more the amount of heat it can acquire from that substance which you are keeping in the evaporator. And ultimately you can see that 4 to 1, this is your evaporation process. Compressor work is not disturbed, but the heat transfer in the evaporator is increased. Earlier evaporation is from 4 to 1, now evaporation is from 4 to 1. This has increased. Refrigerating effect is increased, and ultimately the COP is also increased. So out of this 4, that is reducing the suction pressure, increasing the discharge pressure, effect of superheating, and effect of subcooling, only this method is feasible, and this is possible to get the more COP. So that is about the factors which is affecting the performance of VCR system. That's about the today's lecture. We started with the refrigerations. Okay, second law of thermodynamics also we have covered. Then we have compared the refrigeration and air conditioning. We have gone through the performance parameters just like COP, tonnage of refrigeration, okay, assumptions for VCR cycle, components of VCR cycle, okay, its representation on pH and TS diagram, finding out the values of COP and different factors for calculating or for examining the performance of VCR system. Okay, the subcooling is the process of cooling the liquid refrigerant below the condensing temperature for a specific or for a given pressure. So thanks for watching. The link would be present in the description box for the assignment, and you can post your queries over there. Okay, thank you.